Our next talk is coming to us from Phil Bartie. I believe I got these organizations in the right order. Phil Bartie from Herriot-Watt University and William Mackaness from the University of Edinburgh. They're going to be telling us about using PostGIS to generate real-time descriptions of landmarks and their position relative to the user. Wait for it, for wayfinding without maps. Without maps. We got to run these guys out of town on a rail. You can't come to a mapping talk and talk about without maps.
Yes, it was an interesting project where we were doing sort of virtual agent, trying to guide people around the city of Edinburgh without actually having any map in front of them. So that was kind of the project.
Yeah, the vision is the idea of concealed technology, so that people could just be hands-free and eyes-free to just sort of rove around the town with just an earpiece, giving them all the information they needed. So there was no maps, but of course there was loads of geography underneath that.
Well, let's hear it, and then we'll come at you again with some questions.
Okay,
thanks.
My name is William Mackaness.
And I'm Phil.
And today we'd like to talk to you about a European funded project called SpaceBook. Our presentation is in 3 parts. Most importantly, given that it's PostGIS Day, we want to talk about how we used PostGIS and how critical it was to the success of this project. Okay, first of all, let's talk about the why. It was Mark Weiser who said, "The best interfaces are invisible. We don't notice them." All of us are very familiar with location-based services. The idea that we can use a device to gather information, it might just be about the weather or what's going on in the city, to find something or someone in order to visit or rendezvous with someone. And also we use our devices a lot for navigating to a particular place. What we argued in the SpaceBook project was, however, that the constant interaction with the device actually takes you away from the places that you're trying to explore. But wouldn't it be exciting if we could effectively be eyes-free and hands-free? And so we came up with this idea that we could have just something that was an earpiece, effectively, connected to a geographic-based database.
We are debuting on April 1st the E-Lane. We all know that many people are using the sidewalk, looking at their iPhones, Blackberries, other electronic devices, and they're quite distracted by those devices, bumping into people and other things happening.
Okay, so now I'd like to talk about the what. So as we've already established, the ambition was to create something that was hands-free, eyes-free, something that worked through a dialogue-based interaction. And it was pedestrian-focused. So the context here is that the tourist is traveling around the city, and this device is a virtual city guide. It's telling you about the landscape as you move through it.
So the back end of the system worked a bit like this. The user has a request like, what's the building on my left? We need to turn that speech into text. That's what an automatic speech recognizer does. That then has to be turned into something semantic. So we have a semantic analysis component that tries to understand the request. It gets passed to an interaction manager, and that deals with requests from the user and then finding an answer and returning that answer. So the interaction manager then had a visibility engine to work out what you could see, a city model that was built with Postgres, PostGIS, and a QA system that did things like connect to Wikipedia. We also take the user's input, so a GNSS input, which we put through a pedestrian tracker to improve the location to where they were on the street. And eventually the interaction manager then returns back some text, so it does a natural language generation which gets turned into speech using a text-to-speech engine. And the whole of that process has to happen really sub-second, so the whole thing has to be highly optimized for real-time interactions. One of the interesting things about building a system that doesn't have a map in it but uses spatial data is to think, how are you going to talk about objects in the city? How are you going to describe them? What kinds of things are used in descriptions that you don't find in traditional maps? So these are just some examples of like a Ordnance Survey map there, and the thing corresponding location in Edinburgh. And there are lots of things you notice in the picture which aren't on the map, like the colours of the buildings, the materials they're built from, like brick or concrete or marble or something like that, or particularly on some of our streets are cobbled streets. The age of the building and architectural style, whether they've got a dome on top or the form of them, like they look like a church. What surrounds them, what their relative positions are compared to other objects from this first person point of view, and lots of other things like how they feel, are they cozy or quaint, or and also linking activities to place, such as I'm looking for somewhere to eat, and now you have to link that to the types of things like cafes and restaurants. or I'm looking to play football, well, you can go and play that in the park, but you could watch it at the local stadium. So we need to build a city model, and it has to be more than just a map of data. It has to include all these extra attributes, or as many as we can source from wherever that may be. Another aspect of working without maps is thinking about what people can see from this first person point of view. So we had a visibility engine that modeled features in the city at a polygon level and how much of them you could see. And that was built on using LiDAR data, and the LiDAR data was used to generate a surface model and a terrain model. So this next sequence of slides shows you an example of how the visibility engine could be used to work out which buildings at polygon level are visible to the user as they move around Edinburgh. So another thing you could generate is the skyline. So the blue dot represents the user as they're moving around, and the orange line is the ultimate distance they can see to the horizon in the city. This is going into the old college, part of the Edinburgh University buildings, and it's like a quad. You see the very limited view in here. It's quite useful for building referring expressions, which is how you generate a text description of something. So you could say something is on the skyline. We can also look at the perspective view. So this is looking at the LiDAR data from a sort of first person point of view. So all of this visibility engine stuff was done in a custom application written in C#, and it was calculating things in real time in parallel across many cores. So what this allowed us to do, combining all the city model and visibility engine, is to generate descriptions of objects in a scene like this. So this is the top of the mound looking across Princess Street Gardens towards this building here is known as Scott Monument. And what we can get is from this viewpoint, the application combining city model with its PostGIS dataset and the visibility engine, a list of the ID of the item from the database, its name, whether it was a site or an individual polygon, which we'll describe in a minute what we mean there, but a site would be a collection of polygons. And then a number of metrics, so the distance away it is, the angle it is from the user relatively from their facing direction, and then finally this is a saliency score, which combines a whole load of metrics, including the type of object, how far away it is, how visible it is from the visibility engine, and things like that. So the database, you can look up things like what kind of building it is. We have a number of descriptions in there, because remember there's no map, there's just speech interface, it's a dialogue system. The rest of this is modeled, so there are things like it's visible is modeled by the visibility engine. The fact it's in front of you, that it's tall, it's on the skyline, it's about 300 meters away for Scott Monument, that big object that looks like a rocket ship. And it's downhill from you, so that's all coming from the city model, which is of course handled by PostGIS. The fact that it's behind another recognizable object was also something we looked at. So these are other landmarks, and we talk about landmarks as being visually interesting, semantically salient, and also structurally salient, and structure being like it's at a junction or something like that. So East Princess Street Gardens is visually important, so is the National Gallery, which is this one, and Jenner's department store is one of the buildings over here, is quite famous in the city. So we can then describe where it is from this first person point of view based on those kind of saliency models. This is a demonstration of using it in just to test the interface really. So here I'm typing in that the field of view is going to be 180 degrees and that the user orientation is 0 facing north, and wherever you clicked on this map it then generated live. You can see how quickly this was working, what was visible from that location. So as you enter the corridor of a street, obviously not so much is visible. When you're in the more kind of junction areas you get a larger number of features visible as well.
Let's explore a little bit more the functionality of the system and how this tied in with the various data sets that we used. So here are two essential components. The first is the types of requests that the user might make of the system. Can I see something? Where is it? What is it? How do I get there? And the second component to the system was this idea of actually offering or pushing information to the user. In other words, informing them about what was in their field of view. And for each of these questions, there were two essential components that we were using, either the city model or the visibility engine. And for each of these questions, you can see what's happening. we first of all need to know where that object is, then we're checking for its visibility, and then we're generating a referring expression in order to explain where that object is. And we can do that in the context of, can I see something? And similarly, when we ask the question, where is something? And when we come on to ask, well, what is that object? How might we describe it? And also in terms of how we get to that particular thing. So being able to calculate an optimum route, being able to identify the useful landmarks that we can use to more efficiently describe the pathway that they should follow, and then generating a set of navigational instructions. And finally, there's this idea of being able to push information. So this is where we identify those objects in the field of view that are really salient, really interesting. They might be large or significant buildings. We might order them according to how close they are to the user or where they are in the field of view, and that information is being passed to the user. The data that we needed to support this functionality had to be at the large scale, in other words, of a very fine resolution. And it also needed to be locationally precise. And that's why we went to the National Mapping Agency of Great Britain Ordnance Survey Master Map data, and this provided a polygonal layer. It's 100% coverage, and what we can see for these polygons, they're representing things like roads, pavements, buildings, green spaces. And it's intended to be used at the very fine scale. What it doesn't contain, however, are the attributes, the things that describe what goes on in these places. For that, we used another data set. Well, in fact, we used two. First of all, Ordnance Survey has something called Point X, and we also found OpenStreetMap to be very rich, perhaps not quite as locationally precise, so we combined the attribute information from OpenStreetMap with the Ordnance Survey fine-scale polygonal data. And those attributes gave us information about cafes, hotels, and things like that. And these are recorded as points. But a simple point-in-polygon operation enabled us to associate the building use with the actual polygon footprint. A very important part of the SpaceBook project was the capacity to support the navigation of the pedestrian through the landscape. And so for that we needed a topological network. We therefore used OpenStreetMap for this. It includes not just the road network, but also the pedestrian network, paths and steps. And since the whole focus was around pedestrians, we found this to be a very useful database to use. And we used PG routing to return back the shortest path. And later on we'll be describing how we took that path and then converted it into a set of understandable terms.
So this was what the natural language processing specialists were interested in doing, which is how do you turn this speech request, such as how do I get to Vapiano's Italian restaurant, into something you can then look up in the city model. So this SA component, the semantic analysis bit, turned it into this MRL. Here we've got an idea of the dialogue act, the route is required, it's checking the is named table for that particular feature, it's checking the is a table for finding a restaurant that links to it, and so on. So as William pointed out earlier, we have this kind of structural layer of the city which doesn't change very much, which is the OS master map that describes the building outlines. We also have these other points inside of it, and as you can recognize from this image, any physical object like a building could have many points associated to it. So for example, Polygon ID 1001 has inside in here 1, 2, 3, 4, 5 different points. These all could be different things, such as maybe the address of a flat that's on the second level. It may have something else like the name of a shop that is on the ground level of this building. So one of the challenges for us is, if you're trying to push information to the user, as William described, how do you know which one of these IDs, which piece of attribute information is the most important for this polygonal building? We had to go beyond just looking at the kind of traditional mapping data though. So something like Flickr is quite interesting because people are photographing interesting objects, typically the big landmarks or things which are less ordinary. There were very few photographs of Flickr on ordinary houses. There were lots of photographs of very grand buildings or maybe even run-down shacks and sheds. It tends to be the extreme ends. One of the challenges of using Flickr data though is that the photograph location is not necessarily the same place as the object being photographed. So what we had to do here was map the photograph object identified in any tags to the respective object on the actual map. points shown up in green are all photographs that have a tag of castle in it. So you can see Princes Street is a great location to photograph Edinburgh Castle, as is Carlton Hill there on the east side. And that's because it has good views across the city towards the castle. But what we need to record in the city model is that Edinburgh Castle itself is the photographed location. So this is what the viewshed created, and here we're looking at the concept of a site. So we talked about earlier the difference between a polygon and a site. So a site is a collection of polygons. So I think Edinburgh Castle is something in the order of 320 polygons making it up from the OS master map. And you can see that our city model agrees that these would be good locations to photograph it, as would Carlton Hill over here. So another thing Flickr allowed us to do was to look at which streets were more walked. We could look at where people have taken photographs and then basically rank these based on the most popular to least popular streets. That gave us things like Princes Street is well known, George Street, the High Street, Leith Walk, etc. And this is really useful if you're generating a route instruction and you want to guide someone. Rather than giving them micro instructions, you could say, do you know how to get to Princes Street? Okay, head there and I'll give you the next instruction once you're there. Foursquare was also quite interesting because it allows us to see where people are going. It doesn't necessarily need to be a particularly attractive building, but it could be something that is very highly popular, such as a cafe or a museum potentially. So that data we took and we put into the city model as well, very much to help us in deciding which buildings were interesting to push, and also in deciding which of the many points inside a polygon was the most salient. In terms of generating interesting or natural instructions, something we often refer to as bends or junctions. So we just modelled that by looking at the network dataset, and we looked at where the angle of the road changed beyond a certain degree and considered those bends and mapped that as a new layer. We also looked at the sinuosity, so just the straight length from the start to end point divided by the actual road length between those points. And that allowed us to say things like you need to go down this straight road or down the bendy road. Another interesting challenge is when you don't have a map to look at, but you're trying to narrate someone to a particular location or answer questions about something, is what does the user see from their current location? So here's an example where one building has inside it a couple of very highly salient things. One is Blackwell's bookshop, and another one is Cafe Nero, where you can go and get a cup of coffee. Now, depending on which side you approach from, you get a very different view of this building. So from this side you would see Blackwell's, whereas from this side you would see Cafe Nero. So what we then decided to do was to map where we considered the entrance to be based on, if possible, the actual street address. So for these points that came from the PointX database, we had a street address. So we mapped them from the building out to the road centerline where we thought that would be, and did the same for Blackwell's. Now, if you're approaching, walking down this way, based on the visibility model, you would see Cafe Nero, and we refer to this object as Cafe Nero rather than Blackwell's. So that's again to do with pushing information rather than pulling it. And the big challenge really is turning map data into this first person view of the data set, and how we can see things, not only the colors and materials, but also the arrangement of things like on the left of, on the right of. And to do that, you have to talk about relative angles. So that means dealing from the first person point of view, considering that the user is facing at 45 degrees and the map bearing from the user to their object that we're talking about or they want to get to, maybe a map bearing of 315 degrees, the relative azimuth would be -90, i.e. to your left 90 degrees. Sometimes you need to find a building that's not particularly salient. So this is the hub. This building is very salient, it's a church-like building, but maybe you want to find something opposite over here. So modelling the idea of opposite was quite interesting. So here we take a polygon, we take a road, and then we try and find what the first features are on the other side of that road. So this was the code to do this. So we create lots of functions. So an opposite function that takes a polygon, that's your target polygon, takes a road ID, then uses this idea of a relation with a common road, this function over here, which in turn has this idea of the relative azimuth. So what actually happens is we take the road, we look at the direction the road travels in, and we work out what's on the left and right sides of that road. We work out where the target object is, in this case the hub, and we say not on that side, but what are all the other highly salient objects or the most salient objects on the other side of this line as a divider. So that was all done using PostGIS functions, which of course call on PostGIS. So another interesting challenge was when you're using your phone as a mobile device for working out where you are, it's not particularly good at getting your orientation when you're standing still. So GNSS works well when you're moving from looking at your trajectory, Phones do have magnetometers. They're very noisy depending on the angle at which you hold the device and the surroundings, especially in cities with lots of metal structures. So what we found was a good way of doing it was if the user wanted to head in a particular direction, we'd find the node, the next node in the route from where they were, where they need to get to, and then we'd look around that node for particularly salient landmarks and then direct them towards that. So you might say head towards the hub or keep Castle Antiques on your left and then walk up the street on the right or something like this. So again, we wrote functions in PostGIS to do this. So what this ended up doing is allowing us to produce more natural navigation instructions. So as William said earlier, our PG routing was used to find the route, but then we wanted to turn it into something we can talk to the user about, and we were dealing with pedestrians here only. So the sort of things we wanted to do was introduce this idea of the known street. So do you know how to get to House Street? Okay, I'll direct you from there. Things like, is it downhill? So we looked at the contour layers and we mapped those to work out if the user would be traveling on flat sections, downhill or uphill, which could then be put into the instructions to help them find things. Also how many exits there are at each junction, and the shape of those junctions, whether they're crossways or a Y like a fork, or if it's a T-shape. And of course this changes depending on the direction you're approaching it from. So here, for example, is a junction which is T-shaped from one direction, but obviously not from the direction we're approaching it from. So that let us then turn this into some natural language instructions to get them to the end. And from the user's point of view, the other people in the team, they could call all this power just from doing a simple select command from this function, passing in the starting and end node IDs from the network. Just for interest's sake, we did some of the functions in PLPG SQL, and we did some in Python as well. So you can access Python from inside a Postgres database. Just sort of experimented with both. Finally, before we show you a demo of the system actually working, the other challenge was sometimes the ASR generated terms which didn't necessarily quite match our database. So in terms of how do you spell it? So we added a sounds like function based on SoundX. So there's an extension for Postgres called fuzzy string match. So you can just add that in. We also used the trigram extension as well to look for kind of combinations of words and make them case insensitive. And we used an index based on the GIN trigram operations, which makes that searching very, very fast. So now we'll have a look at some demos.
You see Bank of Scotland in front of you about 420 meters away. It has a green dome.
Yes.
Walk towards Bank of Scotland.
What's that?
That is the statue of Greyfriars Bobby. It is a statue of a black Skye Terrier dog.
Which way?
Turn left onto Lawn Market and walk up the street. On the right side of the road, a few meters away, you will see the Edinburgh Woolen Mill. Carry on straight. You are at the junction between Ladies' Fairs Close and Lawn Market. Carry on straight.
What is that?
That is the Royal Mile. It is in front of you, slightly to your left, a few meters away. It is a cobble street. I searched for Royal Mile. Gazetteer for Scotland says Edinburgh's most famous and historic thoroughfare, which has formed the heart of the old town since medieval times. On the left side of the road, a few meters away, you will see Ness. Carry on up the street. Turn right onto Castle Hill. On the left side of the road, about 20 meters away, you will see the hub.
What is that church?
That is the hub. It is in front of you, about 20 meters away. It is a church-like building on a junction. I searched for the hub. Wikipedia says the hub, at the top of Edinburgh West Royal Mile, is the home of the Edinburgh International Festival, and a central source of information on all the Edinburgh festivals.
We've demonstrated to you how we've developed a system that moves away from the map. But when you do work in a world where you're not using a map as an interface, it requires us to develop all sorts of other ways in which we can support the description of that space. And that has required us to use PostGIS in some really interesting ways. So all of the underlying data is geographical, and yet the actual interaction is completely without any reference to a map. So we hope you found our talk interesting, and we now welcome your questions.
Well, I assume there's a lot of questions. I kind of want to know, like, so you've had people out wandering around with these things in their ears, I guess. How well does it work? Like,
so the biggest challenge is the interaction manager, which is handling the requests from the person and trying to push information, but keeping it temporally close enough to when the data is actually significant. So if you have a long queue of things, obviously you have to keep kind of pruning the queue. So one of the challenges was with that, like the view shed, for example, you could just pass a building. It could be like a tiny street where you could see the castle of Edinburgh, which is a big landmark. It wants to push that to you, but it doesn't push it because it's saying something else. And maybe the interaction manager then starts saying it, by which time it's not important. So that was still an unsolved challenge for us, really. But in terms of like the processing in the background, we got it all to sub-second through sort of indexing and things like that. And it was a set of microservices. So these were running on a bunch of cloud computers and taking various responsibilities. And then this was a group project, so we should acknowledge that other people are involved. We do the spatial bit, but there are other people doing semantic analysis from other universities and people doing the kind of natural language generation parts.
Yeah. It feels like data is a really important part of this, and you managed to get a lot of the data from Ordnance Survey and some from OpenStreetMap. But I wonder, it feels like this kind of thing is a feature that would be nice to have available to civil society, and yet seems likely to be monopolized by private companies that have accesses to their own very good data pools. Is it possible that this kind of thing will just get driven out when the first privately provided systems come online with all the very best data?
Possibly.
That's a good question. I think that was one of the exciting parts of the project, was trying to automatically derive some of that description of data from other sources of data, such as Street View and other sources. So there's still a lot of work to be done. As you can imagine, there isn't a database that records, for example, the color of buildings or the texture of the walls or what they're made of. But we did want to explore that as an idea, the degree to which you can automate the production of exactly the data that you're talking about. Very challenging.
So what's next? Like, this is all very, very impressive. It's hard to imagine something more impressive, but I assume you have something really crazy up your sleeves. What's coming down the pike next?
We've moved on to other things. We've moved on to Twitter analysis in a big way. But the next thing I think is to do this in cars, because actually one of the challenges of pedestrians is they're really hard to track. So we spent a lot of time working on a pedestrian tracker, which is doing live map matching, again using PostGIS. So it's trying to snap people to streets. But if you're going to do a view shed, the street's not good enough. You need to know where they are on the pavement. And so then you're trying to snap. So we have polygon pavements from OS Mastermap. Obviously, we know we're not on buildings, on rooftops, but even that snapping to the right side of the road is quite challenging with GNSS. So that was something we sort of may go back to as a pedestrian tracker and improving that. But a way to get around it is to go to cars, because cars travel in fairly straight directions. They are known paths where they can't stop and turn on the spot, all that kind of stuff. So, and then in a car also, you've got the ability to possibly go to more edge computing. So stick in like an NVIDIA Jetson, run that in the boot of the car to do local processing. So rather than going to a cloud server and having a network, so that kind of thing may be something we start to look at.
I think what we sometimes fail to realize is just how quickly your perspective changes as you move through a city. That one moment you can see something, in a few minutes later or a few seconds later, it's a completely different view. And so that's why for us, the processing speed was so critical.
Yeah, I was very impressed when the directions pointed out a bank 400 meters away, that 400 meters away, that could never work. It turned out to be right in the middle of the streetscape. Like, oh, wow.
Yes. So the viewshed model is doing quite a good job there. I can answer the question live that someone's put about the blind. So yes, we did talk to the Royal National Institute for the Blind about the idea of sort of augmenting a cane. At the end of the day, as you've pointed out, data is so important, and something like roadworks or anything like that, it needs to be literally updated all the time for it to be relevant for them. So they say they'll never get rid of the cane or dog in terms of being able to give that live data. With computer vision, you can do some stuff, obviously. So again, you need sort of edge computing to be able to scale it up, I guess. But we have talked to them about doing stuff like in this kind of space, and also indoors, thinking about indoor spaces as well. But that gets more into computer vision.
Yeah. Well, thank you very much, guys, for this talk. I hope you wouldn't mind hanging around for another 15, 20 minutes on the channel. I'm sure people have lots of questions for you.